All right, good afternoon, everyone. Welcome to our second lecture in COMP1511. I hope you're surviving week one. Please don't panic if things are going wrong in week one. Things always go wrong in week one. We deliberately don't put a lot of material in week one because we know there are students still enrolling, students changing tute labs, students trying to find their tute labs, tutors trying to find their tute lab. If anything goes wrong, the course forum, you should have an invitation to the course forum. That's a good place to ask for help. If it's something private and individual, email the class account. We put the email in the last slide, cs1511@cse.unsw.edu.au for private sort of individual problems, not related to the course content. If it's a problem that everyone's having, the course forum. And you'll notice in the first tute lab is really familiarization of everything, familiarization of tutor with you with your tutor, getting sorted out how you can access C's computers to run C programs and so on. Yeah, so please view the course forum, log into the course forum. As the term goes on, we'll start putting announcements in there, and if they're not crucial announcements, we'll just put them in the course forum. If it's absolutely vital that you received it, we might put in an email as well, but a lot of stuff just goes in the course forum. And you'll see lots of useful answers from tutors in course forums, answers from your fellow students in course forums. Make sure you stay on top of what's in the course forum. First lecture, what did we do 2 days ago? It seems like a long time. It's been very busy probably for you as well as me. We talked about how the course is structured, how it gets assessed, what we'll be going through, where we finish up. You gave my favourite bit, which is doing a bit of history, covering amazing people like Ada Lovelace, Charles Babbage, Alan Turing. You can research those if you yourselves easily online. They're fascinating people. And I recommended the movie, the Imitation Game, as a fun movie, not very accurate historically, but a fun movie to watch. Give you a flavour of what things were like at the very genesis of modern computing. And we saw a first.
A few questions in chat.
Yeah, actually, good point. That's a good point, Tom. Yeah, so questions from the chat now would be a good time before we dive into new content.
The first question was whether there were lecture slides, the lecture slides for today, whether they're posted or not.
I have huge apologies for me. I'm tremendously behind with sorting out lecture slides. I'm actually using old lecture slides that are missing one or two things I wanted to add. I'll add the things that are supposed to be there and put them up on the class web page, hopefully later today, if not first thing tomorrow. So yeah, huge apologies to the entire class. I'm still dealing with a lot of stuff from last term. It's not very satisfactory, and my apologies.
There's another question there about the weekly tests. Also, apparently I'm quite quiet. If you're able to...
let me wind up Tom's volume.
Thank you.
Where is it? That's that one there. Let's wind up Tom some decibels. So weekly tests. Let's not worry about weekly tests. I think you're probably okay. So weekly tests, let's not worry about the particulars of weekly tests. We'll talk about them in great detail in week 3 when the first one comes out. So there's no weekly test until week 3. And then Tuesday of week 3, weekly test, we'll talk about exactly how weekly tests work when we're all focused on exactly what they'll do. But, I mean, yeah, there's nothing you have to worry about now for weekly tests. Any more questions, Tom?
Only that apparently I'm half as loud as you are, so if you mind twiddling the decibels a bit more, that'd be great. But apart from that,
I've wound you up even further. Hopefully that's good.
There is a question about whether people should have received emails from their tutors, which I'll just say most tutors should have emailed you now. If you're in one of the Friday, possible they might not have. But if you haven't gotten an email from your tutor, get in contact with your tutor or send them an email. It may just be that you weren't enrolled or the mailing list didn't include you or something like that.
So it's a little bit of a challenge here, but I think you can find on the course web page your tutor's email, link to the timetable, I think. And tutors have been trying to reach out, but if something's gone wrong, don't panic. No one fails because their tutor they didn't read the right email in week 1, we'll sort it all out. But we should be trying to sort it out, I guess. Yeah. Right. Any more questions, or can we continue?
I think that we are good to go. I think the rest has been answered in chat.
Okay. So we've got couple of people trying to field questions in the chat as well. So if there's sort of more specific things, we'll answer them there. All right. So I want to talk about a couple of things today, which we've got a lecture today and a lecture on next Tuesday, and then we'll go into next week's lab exercises where we'll get you to write more complex C programs that input and output values and make some decisions around those values. But we've got 2 lectures to work through the best pieces of C you need to know for that. So I'm going to go fairly slowly through some of this today, getting up to a program. We'll see if we can complete a program that makes a decision about a value and does something with it. But again, then we'll have a tutorial next week where the tutors will work through this, give you a chance to ask questions about all the things you haven't understood, and then you'll get to try out these ideas in lab exercises next week. One thing to be aware of is that we don't start too fast in this course. One concern is any student can start up until Sunday in any UNSW course. Plus, students with special reasons often come in week 2, so we don't like to put too much stuff too early in a course because these students coming in late, or people that have problems finding tutes and things like that. But then the problem is things really ramp up in weeks 3 and 4. So be prepared to have to do a lot more in weeks 3 and 4 labs. All right.
But do remember that you've got your tutors there, so they'll be able to help out. It's not like a scary ramp up. It's just that sort of the work builds on it.
It's more don't don't plan a ski weekend, a long weekend or something like that for 2 weeks time or whatever. Things are going to get busy, and don't think because this week's lab was easy and you finished early that's always going to be the case. No. All right. Let's talk about storing values on a computer. Yeah, here's where I'm missing some slides. I wanted to say a bit more on this slide. How do we store values on a computer? Yeah, we saw in my my little taste of history, computers, what I called analog computers, where they store the value. We saw an ancient bit of brassware, Greek brassware, where the values were stored as the position of a wheel rotated to represent a value. Charles Babbage's engine did this as well, partly. It was sort of halfway between the Greeks' prediction of machine to predict eclipses and a modern computer. So that's one way to store a value. But the great revolution in modern computing was recognizing the best way to store a value was not as continuously or even as with many possibilities, but store values just using 2 possibilities. And we'll call the 2 possibilities 1 and 0. And if we do all our storage like this, just store things as just one of 2 possibilities, then building computers becomes so much easier. Now, those of you with challenging minds, inquiring minds might be saying, well, why not 3 possibilities? Right? And there's not actually a fantastic reason you can't build computers where everything is stored as 3 possibilities, but it turns out some things work better still just as 2 possibilities. Some of you who like the fact you've got 10 fingers maybe so, well, can't I store things as 10 possibilities? That's, by the way, effectively what Charles Babbage did with the machine that he never really built. The general purpose computer he never really built. He stored things as 10 possibilities. So how do we talk about these 2 possibilities? One way to do them, if you're a mathematical person, you might think of these as base 2 numbers or binary numbers. And you might think about the 2 possibilities you store things as then as 1 binary digit. And that's a contraction of that has come into the whole language really, as bit. So what is a bit? It's just one of 2. It's just 2 possibilities, a binary digit, 0 or 1. And when we talk about a bit in computer hardware, it's somewhere we can save a 0 or 1. And by the way, you should be thinking about, if you think about it, you know already, some sorts of information are lost when you lose power to your computer. Your laptop goes flat, the power plug gets pulled out of a desktop, some information is lost, and some survives. Some stays there indefinitely, even if there's no electricity. So bits get stored in different ways in a computer. We're not going to have, that's not something we can get into this course. You'll have to do subsequent comp courses to really get into that. But to give you a taste of it, how might an electronic computer store these things? It might store, if it's a voltage, it might store a 1 as 5 volts and a 0 as 0 volts. That's classic sort of possibility for representing these things as a voltage on a wire. Another possibility would be the direction of a switch. Now the switch might be semiconductors. In older computers it could have even been mechanical, so it might be a switch flipped one of two ways to store a bit. Alright, let's come back to that. So we have variables that store a value as bits. Yeah, as bits. The value a variable holds will likely be different over its lifetime, but at any one point in time a variable stores a particular value, just one value. There's a gigantic exception to this, which is quantum computers. There'll be no coverage of quantum computers in this course, but they are a completely different world to the sort of programming we do in this course. An exciting and interesting world. Alright. So, what can we store in a variable? C variables have a type associated with them. Every variable in a C program has a type. A type restricts or specifies what values can be stored in them. It's really a set. So it says this is the set of possible values you can store in that variable. The sets are very large though. We'll just look at two types in upcoming weeks. So it's going to be a couple of more weeks, I think week 4 before we see another type, maybe week 5. The two types are a type called int or int and a type called double. They get used for numeric values only. Int gets used for integer values. You're probably sharper at maths than me, but an integer is a whole number. Positive, negative, 0, but a whole number. Double gets used to approximately represent fractional numbers. And that raises all sorts of possibilities. Let's just first talk about ints. Alright. Now, C variables have a fixed number of bits used to store the value. Hence, they can store a fixed range of possible values. How many bits, you say? Yeah, the answer to that's a little complicated, but let's make a simplifying assumption to get us through the next few weeks. We'll get us through mostly through this course. Come back in COMP1511 and this gets explored in great detail. So what we're going to assume is something that's pretty typical for general purpose computers is an int is 4 bytes. Oh, what's a byte though? Yeah, interesting question. Again, the precise definition can get a bit interesting, but for our purposes we'll assume that if you put 8 bits together you call it a byte. And it's convenient in the hardware to group bits in little chunks. It makes building your computer easy. That makes working with your computer easier too if you can talk about chunks of bits. So a byte's a very convenient sized chunk of bits and it's used for many things through computing. So a byte is 8 bits. So if an int's got 4 bytes, it's got 32 bits. 32 ones or zeros. And if you do your arithmetic, that's 2 times 2 times 2 times 2 times 2, 32 times, or 2 to the 32 possible bit patterns those 32 bits can have. So that means we can only represent 2 to the 32 of the integers. Unfortunately, there's an infinite number of integers, so that leaves us with just representing a subrange. Now, the most useful integers are the ones close to 0. So for C, the integers chosen doesn't have to be this way, and do COMP1521 and you can see other possibilities. But for C, if you have 4-byte integers, these will be the integers you can store in an int variable, from minus 2 billion and some to plus 2 billion and some. You want to store a larger integer? You can't. You want to do arithmetic and it goes and gets a result larger than that. It's called overflow, and it's a problem. Get a result smaller than negative 2,147,483,648. Also a problem called underflow. There's one thing I really like here. A lot of this you can figure out. You can think about it logically. And that's one thing. There's not much we can assume about students who come into a computing degree, but generally you're good at thinking logically and mathematically, figuring out little puzzles. One of the puzzles here is, oh look, that number's just one different in absolute value to that number. Why the asymmetry? It's because somewhere in there, there's a number, there's just a single number, 0, which is neither positive or negative. Yeah. All right. Yeah, because there's 0, someone's saying in the chat. Oh. By the way, you can get security exploits in programs resulting from integers being too big to store or too small to store. Yeah, do security courses later on. You get into all sorts of weird and wonderful consequences of these sort of things. So this is why we get to teach you the fundamentals, because they have consequences. They're very important. Now, I've said we're going to assume ints have 32 bits, or you should prefer 4 bytes. It's not on all platforms. There are C programs all around you, even though you don't know it. I've mentioned one. Yeah, maybe if you do your own washing. Some teenagers aren't quite up to that yet. If you do your own washing, the washing machine you're talking to will almost certainly have a C program inside it. It's probably got a tiny little chip that costs about 50 cents, but it's still running C programs maybe to control the washing cycles, spin the drum, turn on the water, turn off the water. It might have 16-bit ints perhaps in it. Now you're saying, I want to deal with huge integers. I don't want to be restricted like that. Do I have to go to another language? Most languages have libraries, extra code you can access. It's not part of the main part of the language where you can have any number of bits in an integer. There's still sort of limits. It depends on how many bits you can store in the memory on your computer and things like that. But you can get arbitrary sized integers and do arithmetic with them. But that's not something for us to worry about now. Oh, right. I think I'm going to see if I can show you bits. So I've actually got here a program that actually comes out of COMP1521. So I'm not even going to show you what's in the program because it contains things we teach in COMP1521, but I've got it set up. I'm going to pop up a window. Yeah, all right. I'm even going to change my prompt. I think you'll probably get a prompt that looks like this in VLab, so I've set my prompt to be the same. Remember, a prompt is there saying the terminal window, I call it the shell, is ready for you to take commands. So I'm talking to a program on a CSE Linux server at this point. I haven't shown you how I connect it in because the way I connect in is a little different to how you will, unless you're running a Linux box, which you probably aren't. So you'll probably this week's Tutor Lab, maybe your tutor helped you get set up to connect into VLab from your laptop. Installing a program like Tiger VNC to do that.
Andrew, there's a good question in chat, which it might be worth focusing on for just one moment. The question was basically saying, if something has 16 bits, then are there 2 to the 15 possible patterns? Which is something I think I see quite a few students sometimes run into. The trick is, if there are 16 bits, then you've got to have, a bunch of positive numbers, but then also a bunch of negative numbers. So there would be 2 to the 15 possible positive numbers generally, but then there are also negative numbers, which means that overall there are 2 to the 15 times 2, or 2 to the 16 possible bit patterns in total.
How we use those, yeah, that's true. First, if you've got 1 bit, there are 2 patterns. 2 bits, there are 4 patterns. 4 is 2 to the 2. 3 bits, 2 to the 3 is 8 patterns. You can figure it out. You can write them down, actually. But we could do things many ways. So you could say we're not going to use negative numbers. Lots of programs don't, and allocate the bit patterns differently. But for the type we're going to use in this course, it's almost symmetric. It's almost the same number of negative numbers and positive numbers. So I've got a program here. I think I've put it in another directory, haven't I? So I created a directory with mkdir. So earlier I did mkdir 1511 and created a directory. And you'll notice the lab instructions each week will tell you create a directory for this, or your weekly tests will say create a separate directory. Generally, when we've got a task, when we're working on an assignment, we create another directory, put the files for the assignment in there to try and stay organized. So so I did mkdir 1511, and it already exists because I did this earlier. And I've put a program in there called print bits of an int. Oh, no, I didn't say where to put the program, did I? If you don't say where, it actually puts in a weird file called a.out. But you just get confused if you let that happen. So you want to say to it, here's my C program, turn it into machine code. So that's what I'm doing at this step. So my C program is here. I'm saying to DCC, take that C program and put the machine code, the thing that you can run, there in that file. How can I verify that that file exists? I can go ls this, and ls will tell me now that file exists. And if you want to be really impress people, ls has an extra argument, an extra option to give you lots of information about a file. And you can figure out some of that stuff at your leisure. Much of this we cover in COMP1511. But there's a nice thing there.
It might be worth noting.
What time there? Sorry, Tom?
Andrew, worth noting. So with the terminal, some people might not have seen this. You can't select to go back inside the terminal. So sometimes you need to use the left and right keys to move left and right to edit the middle of your command. So just there, you might have seen Andrew say he wrote ls print bits of init, then he wanted to add something, so he could use the left key to go left. That's something that some people might.
Thank you so much. So I used little arrow keys there. Yeah, maybe I should have one of those things on the screen that shows you what key you're typing. That might be a good thing to do for the next lecture, actually.
There's also a good question in here about, is learning some of the Unix commands meant to be like a separate part of the course, or is it just a means to the end of learning how to code in C? And I think pretty much in this course, all the Unix commands that you need, and when we say Unix commands, we mean things like ls and pwd and mkdir and those sorts of things. Pretty much all of them, they're only used so that you can code in C. We don't really assess it separately. It's just like, if you're not sure how to do those things, you probably won't be able to do some of the coding in C because you won't be able to open a file. But what we've shown you in the first lecture is pretty much everything you'll need. So there shouldn't be too much. There are some useful things you can learn if you want them. There are different files to copy or to delete, that sort of thing. But you don't need to worry too much if you're not sure about those commands. The only things you'll really need are what we spoke about in the first lecture.
So definitely true. So these Linux commands, there's a couple more, CP and RM. The only ones I can think of, you really, oh, and give. Well, you do it using give, but no, they're not the point of this course at all. They do become the point if you do COMP2041 with me. They certainly become the point there, and things like LS a couple of them like LS and RM become the point in COMP1521. But here they're just things we need to survive, things we need to move our programs around, run our C programs. The point of this course is learn how to write C programs to do what we want. So sorry, this C program is too scary to look at. I will put it on the class website if you're brave. But so let me enter a number. Let me enter. We'll enter 6. All right. It will show me the bits for a 6. So that's just showing you all 32 bits being used to represent the 6. Just to give you a feeling for this. And if you think of this as a base 2 number, you can actually figure that out. That's 2 plus 4 is 6. Let me just show you a few examples. Just to give you, this is to give you the real feeling for what's happening underneath, that there's a certain bit pattern used for every integer. So there's 42, and we'll put in a big number. There we go. And we'll try a negative number. Oh, that's weird, isn't it? And 0. So that's seeing all of these bit patterns getting used to represent inside. That's what's happening inside.
Might be worth just pointing out as well, because there are some questions about like why we're looking at this. In COMP1511, we don't really look too much at what the bit patterns actually are. You don't really need to remember these or anything like that. And even the things about how an integer is stored, they're more so you can understand what's going on. So even if there's an important takeaway from this, it's more just like understanding that these are things which are stored in memory, which you can access, which you can look at, and this is what they look like in memory. But if the particular patterns of things, don't worry too much about that, because that's the sort of thing you can pick up in other courses, like Andrew was saying.
So there for someone in the chat was 660 and 600. Yeah, so this becomes the stuff of the lecture, of the course in COMP1521. We go into representations. I think that's enough for that program now. Oh, so I want to terminate this program, and this program doesn't actually stop. There's a special trick. I'm holding down the control key that says CTRL, and I'm going to hit the C key, and it will interrupt the program. And DCC actually gives me some extra information saying this is where it's up to. Don't worry too much about that. In fact, we're about to explain what a little bit of that is, but that program is way too scary for now. So let's come back. It
might also just be worth pointing out, if you're the sort of person who does have that inquisitive mind, considering perhaps why would -1 give you all ones? It's an interesting question, which we don't cover in this course. But if you're sort of thinking you want to go and do some research on your own, that'd be a very interesting question to go and look into.
Yeah. That's that we cover. Well, we half cover in COMP1521, but until you actually build your own computer, you don't really build your own arithmetic unit. You don't really understand. All right, integers, yeah, they're okay. Real numbers are even more scary. There are lots of consequences here.
And when we say real numbers, we mean numbers that have a decimal point after them, not necessarily real numbers as opposed to fake numbers that you might find somewhere.
All right, so fractional numbers. You might be wondering, why is the variable type for fractional numbers called double? It's because it's 8 bytes, which is 2 times 4 bytes. Is that a stupid reason? Yeah, it's pretty stupid, but it is what it is. So 8 bytes are used to store doubles. That's any general purpose computer, and pretty much any computer, not all any computer, but very ubiquitous these days. So 2 to the 64, that is such a huge number of patterns, a gigantic number of patterns. But there's a problem there. If you talk to your maths lecturer and ask them, how many real numbers are there between 0 and 10? How many real numbers are there between 0 and 1? Between 0 and 0 and 0.1? And there's some very bad news there about real numbers. So we have to approximate. And we can't even approximate over a range. Or at least for integers, we can say, yeah, between x and y, I can represent all the integers. Not with real numbers, because between any x and y, there's an infinite number of reals. So we just have to pick points we can approximate. And it turns out the way we do it, and this is just to give you the flavor. These are not facts that you should be memorizing, not something you should be getting a tattoo of, definitely. Talk to your tutor before you get anything tattooed about the course. Actually, don't even talk to the tutor, just don't do it. So the tiniest real number we can represent is 10 to the minus 308. The biggest is 10 to the 308. They're pretty good for most things.
It's worth noting that there's going to be a theme in this course, particularly in the first few weeks, of numbers not working the way that you expect them to. So we talk about here approximation errors. Turns out that 0.1 plus 0.2 is not equal to 0.3 on a computer because of doubles. And in a similar way, division sometimes doesn't work the way we expect it to. So even if you've got your PhD in maths in COMP1511, even if you're terrible at maths, don't worry, because in COMP1511 maths works a little bit differently and you can learn that instead.
All right. Yeah, we might. I've got some programs to show you these consequences, but we might leave them for now and come back to them. Let's try and let's give you some good news, the things that work easily and well. All right. So, variables have to have names. So I specify a variable. I need to say what type it is, and then I give its name. So that's a variable declaration. That's saying to the C compiler, my message to the C compiler is, I want to store a value. So you've got to put aside 32 bits somewhere, whatever size an int is, 4 bytes somewhere to store an integer value. And I'm going to refer to it as answer. So I've got to give it a name. Name, by the way, choosing good names is famously one of the hardest problems in computing. And this little program, we can come back to it. I can assign a value to it, and that's an example of assigning a value to it. And this is an example of outputting it. Don't worry, we're going to go through these things in a few ways. But I think I've got a slide about names. Yeah, I wanted to say something about names. You're restricted about what you can, characters you can use in a name. So letters, digits, and underscores are pretty much what you're allowed to use in a C variable name. You should use a lowercase letter to start your variable names. Crucial thing to be aware of is C is what we'd call case sensitive. That means if I use a capital E instead of a little e, I get a different variable name. Do we want that? Yeah, it's an interesting question. I'm not just, you could design the language so that the case didn't matter. And you certainly see that in some places in computing. In some places in user interfaces, it's very desirable. If someone has to type something in on a phone, insisting on case is a bit of a pain for them, so you might not there. But for a C program and coding, this is probably a good decision. But it is the decision, so you have to be aware of it. And it's the case for most computing languages that variable names are case sensitive. There's a trap. Certain words can't be used as variable names. Well, what are they? Well, I'm not going to tell you. No, it's the DCC. Fortunately, is smart enough that it'll tell you. It'll tell you if you've used one of these words. But the words are words that are associated with special meanings in the language. I'd call them, keywords. So, and we're going to progressively introduce you to these keywords as we go through. So when we get to talk about while loops, you'll meet the while keyword. But And until you've seen some of these keywords, you might accidentally bump into them. But DCC should be nice enough to be able to tell you, you can't call a variable that, rather than getting very confused. You're saying, why? Well, why can't I have a variable called double, even if it is the name of the type? It's because it makes it too hard for the C compiler to work out exactly what your program means. You use the word double elsewhere in your program. Do you mean the variable double or the type double? If you use the word while, do you mean the keyword while or the variable while? So you just told you can't have these as variable names.
You can imagine the chaos that would happen if you said int 3 equals 4. That might not work too well.
Let's talk for a few more things, and I'm going to switch to trying out my coding skills. All right, so in this week's lab, you're having fun getting set up with VLab and compilers and CD and McDear, but we're not doing very exciting output. But you're doing something like printf hello world to get some characters to appear on the screen in the terminal. What do I have to do if I want the value of a variable to appear? So if I have an int variable called num, how do I get its value on the screen? Printf can do that for me, but it's in a special way. It's a two-part story. Again, I give printf what I'd call a string, but when I want the value of num, I put a little %d there. %d says to printf, interpolate a value, add a value there. The d is decimal, by the way. Print out an integer base 10. There are other possibilities. You're probably happy in base 10 though. Print out an integer in base 10, and that will follow further on. So printf sees that and then looks further on and sees the name of the variable and prints it out. We should try this out, I think.
One thing to note with this is you only ever use %d in the context of printf, and then we're also going to talk about a thing called scanf in a second, but it's only ever within those quotes. %d isn't a thing that exists within C itself. It's only a thing that you can write when you're printing, or as we'll talk about later, scanning. So that's one thing that really catches some people out. One of the best ways of thinking about %d is just think about it like a blank. So you're saying, the value of j is blank. And if %d, that means that blank will be a decimal, so a number in base 10. And then afterwards, you specify what should fill in that blank. So %d, and then afterwards you would say num, and that says you should fill in the first %d with num. So there's a question in chat, for instance, about saying printf j something something. J is just a letter. Printf doesn't know that j is a variable, but if you said printf %d is, then you would need to, then it would fill in the %d. If that makes sense.
Let's try out some of those possibilities, but let me show you a useful trick here. So we managed to write a correct C program here. We want to reuse some of the things in that program in our new program. So let me take a copy of that program. I'll use the CP, which is the file copy program on Linux. So I can go cp hello.c, and that's created printing.c, a second file. That's created printing.c, a second file which contains the same contents, and now I'll change those contents, and I'll use gedit to do that, and we'll explore some printfs. Oh, there we go. So I'm in gedit. There's my program. Let's make my gedit a bit larger. I like large windows. Oh, okay. All right. Let me change my comment to say printing integers. There we go. All right, let's see if I can declare a variable in, in what we call our first variable. I don't know, we'll call it Ada after Ada Lovelace. There we go. All right, generally this is a bad idea. If you name variables after people, pets, girlfriends, favorite breeds of dogs, you can't remember what's stored in them. So it's and you start reading your program. Okay, there's one variable in the program, that's not so bad. If there's 10 variables in the program, remembering what's stored in which variable is going to be chaos. So we choose names that suggest what's in there to make it. Well, it's certainly for your tutor or anyone else reading the program, but it's also for future you. And when I say future you, I don't necessarily mean 6 months time you or 6 years time you. It could be 2 hours time you. So you'll get confused about what's in your program. But we're just playing here, so I don't really have a meaning. Now, I think Tom gave a hint in the last lecture saying don't enter 10, 20 lines of C and then go and compile. Try and compile when you've just done a few lines and see if they work. The less lines you've added, if there's a problem, the easier it is to find. So we like to limit the scope for these things. So sorry, I'm just rescaling Windows. You're saying, Andrew, you're not used to this environment. No, I'm not. I never use this environment. I have a very particular setup on my laptop, and you'll find you talk to your tutor, and they'll have a very particular setup they use for coding, completely different to the one I use, of course. And if you talk to a different tutor, they'll have a different setup. It's a very personal thing. So I never use any of this, but it's what you're using, so we're doing it to show you. All right. So I'll try and compile. Have I saved? Oh no, I haven't. If I look up here, by the way, here's another power user trick. gedit puts a little asterisk there to say I haven't saved the file. And I can save it just by typing Control S in there. And I've lost my gedit. That's a little weird. All right. And I've somehow killed my gedit. All right, we're back. All right. Anyway, let's come over here. Let's compile printing.c and see if it compiles. Oh, it's telling me I'm not using Ada. All right, that's okay. We haven't got very far, but it seems to like everything else there. So let's assign Ada a value. And again, save. And recompile. I'm using the arrow keys to find the last compile line. And now DC's warning me saying, oh, well, you've assigned a value to Ada, but you've never used it. Strictly, that's not an error, but it's saying, yeah, but it's worried that I don't know what I'm doing, or maybe this is a mistake. It's saying, well, look, this is a real C program. This is a fine C program, Andrew. But on line 8, you put a value in Ada, but you never do anything with it. What's the point? All right, so let's see if we can print out Ada's value. We'll put a %d there and put Ada there, and we should be able to print out Ada's value now.
It's worth having a think about what you expect we're going to print out before we see it. Have a think now. What do you think this program is going to print out?
Exactly what characters will appear on this line? Yeah. And there we go. So the %d here, printf sees this as a gap to be filled, and where does it get the value? It goes here. All right. What happens if there's more than 1% D? What will happen there? Recompile the file. Yeah, remember, save, edit, save, compile, run. But I don't get to run. DCC says, look, this is not making a lot of sense, Andrew. You said fill this gap and fill this gap, but you've only given me one thing here to fill the gap with. All right. Let's have a second variable then. We'll have a variable called Charles. Continue our little historical theme. And we'll find to Charles. -67. And we'll print out Charles's value. Save.
There's a good question going on here.
Machine code and run. Let me just see if my program works, Tom. My suspense. Sure. It works. Interpolating two values, the %d and the %d, from the value in the variable Ada and the value in the variable Charles. The question. What's the question?
The question is, well, if I only put Ada once, could it just fill in both the %Ds with Ada, or how would we fill in Ada twice?
If you want both %Ds filled in with Ada, you have to put Ada twice. And it seems a bit stupid, but you have to do that sometimes. Yes, sometimes you want to interpolate a value two places. And I can do that.
It might also be worth pointing out, and I'm not sure if you were going to do this next, Andrew, that those variables that we've got there, you could, if you wanted to, because a variable, one way of thinking about a variable is just sort of, it replaces the text Ada with whatever its current value is. So in this case, if Ada is 42, both of those words Ada will get replaced with 42. You could think about it as just writing in comma 42, comma 42 as well. So it's not necessarily just a variable. You could also put in a number, or even, and we'll get to this later, a calculation as well.
All true. Now, I don't know if you're watching there, but here's a classic mistake, which you'll make as well. I forgot to compile my program, so I saved it, but didn't recompile it. So I ran the old machine code for the previous version, which printed out the value of Ada and Charles. I've then recompiled. Let's run DCC. And DCC is saying, Andrew, oh look, you've got a variable Charles, you even put a value in it, but you never do anything. What's the point? Are you confused? Is there a problem? Generally you should fix something like this, but I've been brave and I've actually run the machine code, and there it's printing out Ada's value twice. Tom was pointing out I could put a constant value there. That's a possibility. Yes, I don't know why DCC is giving me that message. Sometimes these things happen. It's a little weird. Oh.
So these are errors from Gedit, I believe. So Gedit.
Oh, sorry, no.
Does that.
Gedit, yes. Do you know why Gedit's giving me that error?
Yes, I'm told that it's because we're running an old version of Gedit that's not easily fixed. So if you ever see those errors, the easiest thing to do is just press enter a few times, and the error will
pretend they never happened.
Yeah.
All right. So yeah, there is a, you can get, it's good to understand, for example, look at warnings from DCC and understand them, and that's good for learning to program and learning to code. But trying to understand every error message from every random program we happen to be dealing with, that will leave you drive you crazy. So you have to accept sometimes that other programs we're using produce weird, strange error messages that probably don't matter. If you're worried, chat to your tutor, but don't, instead of working on the lab exercise or whatever you're supposed to be doing, focus your time on trying to figure out why gedit is giving this strange message.
I think there's a general bit of advice in there as well. Sorry to cut you off, Andrew, but if you are having trouble, especially if you're in a lab, your threshold for asking your tutor, don't sit there for half an hour trying to figure something out and thinking, oh my goodness, how am I going to fix this? It's good to spend a few minutes to try and solve it yourself, because that's great. But if you spend 5 or 10 minutes stuck on the same problem, always a good idea. Ask your tutor, post on the forum. Sometimes even the act of asking the question can solve it. You'll phrase it in such a way and you'll think to yourself, hold on, I've just answered my question in how I phrased it. That's useful as well.
So a lot of what we do is solving problems that aren't directly how to code something in C. So we have to. There are lots of slightly less related but slightly different things we have to figure out how to deal with in this course. But by all means, sit there for a couple of minutes trying to solve the problem. And that's good for you. It's not good for you to sit there for 30 minutes bashing your head against the wall, and that's why your tutor's there. So yeah, as soon as you've been stuck on something for a while, it's time to take a step back and get help from your tutor, post on the CAST forum, do something. All right. Have I saved this? Have I recompiled? I'll recompile again. I'll run my machine code, and I should see it print out 42 and 2 times 42, which is a large number. Oh, it's 84 apparently. There we go. All right, that's quite nice. I've got a little bit of time before the break. I'll show you the alternative with a double. So we'll change Ada's type to be double. So I've just made a change. Now the C compiler will now set aside 64 bits for Ada to represent approximations to fractional numbers, floating point numbers, call them what you like. Numbers that are not whole numbers. Well, you can also represent whole numbers, but this will be okay. C will see, yeah, I can store 42 as a double. This will not be. And DCC will give me a warning, and let me show you the warning from DCC, and then I'll show you how to fix it. Let me save my file. And see the warning from DCC. DCC is saying, oh, it's trying to help you out here. It's saying, it's pointing at 2 parts of the printf that are wrong. All right, %d says expect an int and print it out decimal, base 10, which is almost always what you want, until you get to a later course. But the trouble is, DCC was saying, oh, what's the corresponding value? Oh, it's Ada. What's Ada's type? Oh, that's not an int. Then you might say, oh, it should do a conversion. Yeah, C doesn't work like that. Other languages might. C doesn't work like that. It just says, no, you've got to make those match. For now, the only way we're going to do that is change what's expected. If you want to print out a double, put the letters %LF there. The whole story here is a bit complicated, but the best thing, the thing that's going to get you into the least trouble in the next few weeks is to think of %LF as matching a pattern for a double.
You can. One of the ways that I like to imagine this is if you've got. I spoke earlier about sort of like a hole in the string where it says, Ada's value is blank. You can imagine that %d is an integer-sized hole and %LF is a double-sized hole. And of course, you can't put an integer-sized thing in a double-sized hole. You can't put a double-sized thing in an integer-sized hole, which is why it gives an error. And just because there were questions in the chat about it, %d stands for decimal, which is a number in base 10, and %lf technically stands for long float, which means like a floating point number, but a big floating point number. In other words, it stands for double. Yes, they're a bit weird, but they only happen in the context of printf and also scanf, so you don't need to worry too much about them outside of this particular use case.
That was lovely. Thank you, Tom. Let's see what my little printing program does now. Ada's value is 40.2.00000. Yeah. By default, %lf prints out 6 decimal places. You can modify that. We won't go into that for now. It's not hard for you to find out if you want to. But let's put a fractional value in there. Let's put in 42.376. Oh, actually, no. All right. 3.159. Oh my God, I can't remember any more than 2. Someone else, quick in the chat, some digits of pi.
I mean, any digits would work, but 3.14159 should do.
3.14159. There must be someone in the chat who knows more digits than that. All right. I guess there's a bit of a delay. All right. Let me save that and print that out.
Now all the pi enthusiasts are posting in chat.
Excellent. There's nothing better than you've come to the right course if you like pi. All right, so there's a fractional value of printing out. All right, so that's 3 o'clock on the dot. So we've started our journey with variables, naming variables, printing out the values in a variable. In the next hour, we've got to look at inputting a variable from the terminal and then making a decision on the variable. And making the decision on a variable will be the focus of next week's lab. We don't have to get through it today because we've got another lecture next Tuesday before next week's lab, but we'll try and start on that journey today. So we're going to take a 5-minute break, and you can get up and stretch, focus at a different eye length and so on, or think about these issues, and we'll get back to you. Feel free to put questions in the chat. Not the best of them I'll answer in 5 minutes' time. All right. Hi, everyone. We're back, hopefully. And ask Tom in a second if he's there. Other things I want to cover from the chat. I was going to say, yeah, some of the stuff we talked about in that at the start of the first hour about bit patterns and limits and representations. Yeah, it won't make sense now, but it's important to start thinking about it early. We're going to work through some simple sort of examples where it doesn't matter that much, but you just keep thinking about it and hark back to it, and you think it may make more sense as we go on. So in this next hour, it's going to be very practical about working through the pieces of C that we're going to put together to write little programs in next week's lab that make decisions. So one thing I wanted to mention is, %LF. You're saying, is that good design? How does that make sense? As I want to print out a double, I say %LF, and what the hell? Why %D? That seems like D for double. Why is it D? Wouldn't %I be more easier for a first programmer to remember? Yeah, that's all true. And there are lots of these little confusing things. These won't trouble you in the long run. We'll get to harder, much more conceptual issues as the weeks go on. But these little things, they'll annoy you for days. But you'll just see the message, you'll fix it. You'll see the message and fix it. You'll sort them out. But there are lots of little annoying things that you'll have to wrestle with in next week's lab. Let's modify my program back to being an integer. And we'll just put, say, 3 in Ada. And print out Ada's value. Let's just compile that. Ooh. Let's save it. And run. Lovely. All right. I wanted to show you Printf's friend, scanf, the inverse of Printf, which I can use to get a value from the terminal into a variable. Let me show you it in action. So the function is called scanf. One of the keys to succeeding in COMP1511, computing degree, working with computers even if you're not going to be a coder, working with computers if you're going to be an engineer, working with computers if you're going to be a scientist, a biologist, is learning to spot patterns without being told, without having to look things up, spot the patterns. So you might spot, you have function names and 2 round brackets and a semicolon, and that's the rule, more or less. You infer, induce is probably the technical term, this rule. So you've got to, rather than having to be told every bit, you've got to look at some examples and infer these things. It's the way to be able to work with computers much more easily. Now scanf looks a lot like printf in that we have a little string there with these percent specifications. So we say %D, and it has the inverse meaning. It's meaning I want an integer coming in, and you have to specify a place to put it, and you do it in a weird way. You put an ampersand there in front of the variable. We'll explain why in about 5 weeks, 4 weeks I think it is. It takes a little while to get to the point where we can explain why you put that ampersand. For now, you've just got to remember, that's how a scanf looks like. And there's nothing wrong with, if you have to do this in the lab, going to the lecture notes, going to the tutorial, whatever, and just copying it there. Or once you've done it once, just copy it to your next program. It just has to be, to some extent, magic for now. Let's try that out. Wait. Sorry, this is accidental. Let me save it and try it out. Let me save it, recompile and try it out. You'll do this as well. But It's just embarrassing.
Totally
You've only been
intentional, of
programming a
course.
week. Sorry?
It's totally intentional. So
Yes, totally intentional.
just experimenting. Make sure the computer knows what it's doing.
All right. Here's a classic problem: is I'm here looking at this program and nothing's happening. I'm thinking, why? What? Why is nothing happening? Why is my program not outputting anything? I can actually find out where my program is by typing Control-C. It will interrupt the program, and DCC has extra code inside it. It adds extra code to your program. So it says, if it's interrupted, tell you where it was. And it says, oh, this is where it was up to. It was doing the scanf, trying to input a value. Right. So there's a message there. Don't leave the person running your program sitting there looking like an idiot, waiting for the program to do something. Tell them what's happening. Put something out like this into a value. I've saved it. I've recompiled.
Shrey has made a good point. Not everybody might have noticed this. I think you mentioned it earlier, Andrew. But you're using the up arrow to go back to previous commands, which is really useful. So you can use left and right to sort of go along the command and to sort of insert something in the middle, but up and down let you go forward and backward in time.
Just bear with me for a second. I'm just going to go over, see if I can. There is a program to do that. This may end badly, but I'm trying to run a program that shows everyone what key I'm typing. And it doesn't seem to be working. Oh well. Oh wait, we'll try typing a key then. Alright, I'm back here on this screen. You'll notice we've now run a printf here to say print out a value. And now the program's in the scanf trying to read an integer, because that's what I asked for, from the keyboard. So I'll type in 789, hit return, and there we go.
There's an interesting observation that somebody has made in the chat here as to why, normally when we've done a printf so far, we've put a \n at the end of it. But why haven't we put one at the end of the printf?
Yeah. And you could, but it just sort of looks nice is if it says enter a value, and then I can just put it there. You could put 3 new lines there if you wanted, but it just wouldn't look as nice. Wait a minute, let me do that. I'll put 3 new line characters there. Save.
It's worth asking then, Andrew, where does the enter come from? If you haven't got a \n anywhere in your program, how does the enter happen?
Because enter, what enter does is produce, put output on a new line. So I'm hitting the enter key on the keyboard right now after the 789. Sorry, my screen echoing program did not seem to work, so I'll have to debug that later.
The life of a programmer, debugging things.
Yes.
They do say that you spend 10% of your time writing code and 90% of your time fixing code. So.
All right. Oh, that's pretty good. That's entering. Sorry, that was showing you a different printing sequence. So I put 3 new lines there, which is a perfectly fine program. It just doesn't look very nice. It says enter a value, puts out 3 new lines, and then I type my value. So it's worth, by the way, experimenting with all sorts of little programs like this yourself, trying out things, seeing what they do. We all get different understandings of what things are doing, and only by writing a program, trying them out, will we discover that our understanding is wrong. That's pretty good. All right. If I wanted to enter a double variable. If eta was a double variable, I would have to say %lf there to say that, %lf here, and you'd have a similar program. Oh, that gives me an idea. All right. So if I wanted, I'm watching a lot of US TV programs where they talk about temperatures in Fahrenheit. I've now got the bits of C to do a conversion from Fahrenheit to Celsius so I can understand what's happening in these US TV shows I'm watching. Yeah, so I can do this. I can write my program, say enter temperature Fahrenheit. Like a space there. Enter that. I'll have a variable called Celsius. Now, temperatures are continuous values. Temperatures in Fahrenheit, temperature in Celsius, continuous values. So doubles the appropriate type there. And then I have to do the conversion. Celsius equals, I can't remember what it is, Fahrenheit. Now C gives you the usual arithmetic you'd expect. So let's look at that. Fahrenheit minus 32. And it's 9/5 times that. Is that right? No, it's 5/9. I think that's the rule. It's not really the point here.
Worth noting that if you were looking this up, we'd probably give it to in a lab. But one of the things that you often would do in quote unquote any program you're writing on yourself, I was going to say the real world, but it's of course the real world, would be open up your best friend, Mr. Google, and have a look there. So a lot of what programmers do in outside of COMP1511 in particular is go on Google for the part of the solution that they're looking for.
So I've misspelt Celsius. One pro tip is don't choose variable names that you can't spell or that are hard to spell. In this case, I don't have a lot of choice. And I forgot a semicolon there. All things I did accidentally, by the way, so don't be surprised if you make more mistakes than that. That's why we have editors. Right,
probably also a good question to ask at this point, Andrew, is like, how do you've mentioned some bad things about variable names, but what's in a good variable name?
Short, gives you a clear understanding of what the variable does. Conveys something about, yes, I'm not sure I've ever really mastered that. All right, let's try this out.
It's a hard skill, that one.
I haven't changed my program name. All right, enter temperature Fahrenheit. All right, so if we're given 75 in Fahrenheit, oh, it's 0 Celsius. That's a bit weird. I don't think that's right. I think 75 Fahrenheit's about 20 something degrees Celsius. What's going wrong?
There's also a question here. Wouldn't using Google technically be plagiarism? Which is an interesting question and good to be thinking about. And this is the sort of thing where you'd want to post in a forum or something to double check. But if you're looking up a formula, do you want to answer it, Andrew?
Oh no, yeah, so it's a good question. So normally would give you the formula if this was an exercise or an exam question or a weekly test question. We'd say this is the formula. The mathematical formula is X. Turn this into a C program. In real life, of course, you'd often be researching the formula and turning it into a C program. But if what we want from you is a C program, it's probably not plagiarism, but you'd still credit the source of your formula. So the important thing is credit. So if you've got the formula from web page X, you got it from Wikipedia, a comment saying, using the formula from Wikipedia, I did this. All right, there's a difficult thing here, which is this bit here. The 5/9 division. C division catches out every new C programmer. So what C does with integer division is turns it into another integer. So C sees whole numbers here and says, oh, Andrew wants a whole number. And what's the whole number I get? The whole number I get in this situation is actually 0. So that's a trap. We'll come back to that. So we'll talk about that in a bit more length at the start of Tuesday's lecture. But my way out is to make it clear I'm talking about fractional numbers, and I'll get a double result. You're saying, how would I have figured it out as a beginner programmer? Oh, not easily. So there's no logical way you coming into COMP1511 would expect that. No. Even coming from other languages, coming from some languages, you might get caught by surprise here. And what every language does with a division differs. And even what they've done over time differs. So Python has changed how it handles division over time. So I think Perl has as well. So languages, there's this very arbitrary choice, and you as a new C programmer have got just no way. It's a good thing we have a course forum and a tutors.
It's worth noting though, Andrew, you probably wouldn't be able to figure out exactly why this was happening, but one of the debugging tools that you've just learnt today that will come in handy for you for the rest of your programming career until you're 120 is that if something doesn't make sense to you, break it down into parts and print it out. Oh. So there was a question in chat that said, what exactly did it do? Like why is this wrong? And if you're trying to figure that out, what you might want to do is you might want to say, well, if I print out the whole of Celsius, that's 0. So then, okay, something's gone weird here. And then you can print out, okay, so what's 5.0 divided by 9.0? And then what's Fahrenheit minus 32? And maybe what you'll find is that Fahrenheit got scanned in wrong, or maybe what you'll find is, oh, hold on, why is that 0? So you can answer those sorts of questions by breaking it down into parts and printing it out. We call that Printf debugging, and it is a technique that will serve you well for your entire career in programming.
All right, so I'm going to come back to Tom's point. It's an excellent one, and the question from the chat. But there's showing you the working program. So I can enter any, so I can say, oh, it's minus, I'm sorry, I have to run the program. But we've got a working, useful little program. The US TV shows, says, it's cold outside, it's minus 20. I can look that up and discover, oh, that really is cold. That's minus 28 in real temperatures. Or they say it's hot, and it's 90 degrees, and I can look that up and, 32, that's not that hot. So that's a useful little program using the bits we know. Yeah. So what was? Yeah, there's a thing here. I've got a problem. Let's go back to the program here we had with a bug. So let's go back to the situation I jumped over and look at debugging it. So I entered in something I knew. I knew that 78 in Fahrenheit is not 0 in Celsius. So what do? I've got to get some information out of there. What I might do is add an extra printf in. Well, I could try simplifying it. Yeah, so what am I trying to do? I could try and go to a simpler program illustrating the problem. I could actually get rid of this scanf, couldn't I? That's one way to simplify the program and say Fahrenheit is just 78 always. Try and get a smaller program. That's often the students won't do this, but often the key is to take your code out, put it in a separate file and run it. So I'll take a copy and work on it. So I could reduce it like that and say run it. Oh, sorry, I could save the file. Let me even simplify it further. There we go. You can assign a value to the variable on the same line you declare it. You say what it is. You can say, I want a double variable called Fahrenheit, and here's the first value it should have. It's actually a good practice. So let's try that. Right, so I've got a simpler program that's still showing the problem. Alright, so I could simplify it again. Work my way down and say that's 78 minus 32, that's 46. Alright. So this sort of logically, not knowing what I'm doing, but trying things, taking steps. Oh, I'm still getting the answer. 5 nines times 46. What's going on there? And then I could say, well, let's just get the 5 nines. In fact, we get rid of all of this text as well. Try and get a really simple program illustrating our this. So we're down to a tiny program that doesn't quite do what we expect. And then we just make a change to it. And we can see a different behavior. So there are principles here which we're just starting to get into. But I wanted to show you this for 2 reasons. Tom mentioned it as a debugging technique. We've got a program that's not doing what I like, and maybe we've got 20 lines of code. If we can simplify it down to just 2 lines of code, 1 line of code, then we can figure out what the problem is. Maybe we put those in a separate file in a separate program and figure out what's happening. But there's more. If I want to understand C, I want to explore, and it's great to write tiny programs and check that they do what they do. And it's a real mark of a successful student who sees something in a lecture or tute and then writes 4 or 5 other little programs. There might only be 2-3 lines that are variants of it to make sure that they understand the general lesson they've been given. So they think, oh, what I've been told, the general idea is this, so I'll try doing it in forms B, C, and D and see if it works. And if it does, great. And if it doesn't, they've learned that they've got a misconception which they have to fix up. There's another way this happens a lot, by the way, is in bug reporting. If I've want to tell someone about a problem with their program, they want a simple way to reproduce it, and you do exactly something like this. You try and reduce the problem to something tiny that you can email to them or report as an issue. So this is something that people in computing do all the time. They've got a bug, but then they try and simplify it and reduce the conditions. All right. All right, let's take a step back. I wanted to start working on another problem. I want to work on a more general problem. Actually, let's put my program back as it was. Go back in time. All right. I'll save that program. Take a copy of that program. That was printing. I've been calling it printing.c, which was silly because it really should have a better name like Fahrenheit.c. So I'll copy it over. I want to try a different thing. I want to write a program where where a user tried to roll a particular value with dice. So we can't do the randomness ourselves yet. So we'll get the user to roll a dice, then enter the values into the program, and then we'll tell them, the program's got to tell them, have they rolled the secret value. It's a nice example of what that's will lead perfectly towards what we have to do next week. So I'll call that dice.c. I'll copy printing to dice.c. Oh, no, that's not the only way to do it, but we'll open it with gedit. So we've got, let's put a statement up here. So the user rolls 2 dice and enters the value. Okay. Alright, we're going to need printfs, scanfs, but it's going to take a different form. Definitely not going to need a Celsius variable, we'll get rid of that, but we're going to need printfs and scanfs, so it's going to be that general form. I've put a comma up there to say what I want to do. Right, so dice, I guess 6-sided, 10-sided, 20-sided, your choice, but they can be stored in an int. So we might have int for dice 1. You can declare them on 1 line, but let's just do it on 2 lines. Let's say enter dice 1. And we'll scan in an int, so it's %d and ampersand dice 1. Ooh. We'll copy that. Will that work? Enter dice 2. Oh, that's it. Be nice not to have to repeat that code, wouldn't it? And there is a way, but we haven't got it yet. I want that printf, but not yet. Let me show you a trick. If there's code that you don't want to compile yet sitting in your program, I can turn it into a comment. So I put the / there, and that says to the C compiler, just ignore what's left. Could be English, could be anything. Up here it's English instructions, but down here it's actually just, it happens to be C, that just C I want the compiler to ignore. That sort of shows you how comments work. Alright, this is not our complete program, but it's reading in 2 values, but let's try it out before we go further and see how far we've gotten with this. Oh, compile first time. Oh, let's run it. Not the version I haven't saved it. I apologize. Compile again. Run it. Enter dice 1, 4, enter dice 2, 1. Alright. Next thing would be to sum the values. Alright. Arithmetic works how we'd expect. I can declare an int variable. We'll call it dice. It's nice to use multiple words in names, and if you use it, you can put an underscore between them to sort of segregate the word out so it's obvious how it reads. If I call the variable dicem, it's a bit hard to see what the words are, but if I put an underscore there, it's nice to read. We don't actually want to print out the sum. We want to check if it matches a magic value, a secret value. But it's quite common when we're coding to write code to let us test the code we've written that we won't actually use in the final version of the program. 5 minutes writing code to test what we've already done before putting the results of that code into more code can save you 5 hours of debugging sometimes. So let's put a printf there, and you'll often hear these called debug printfs. We're outputting this just to see what's happening at this point. Someone's asking in the chat, shouldn't they be checking what value is being read? Yes, that's a crucial part of coding. A prudent programmer right here would be checking what value they got. Was it a valid value for a dice? Had they entered a negative value or something like that? Will that break other parts of my program? But we've got to walk before we can run, so we'll leave that for now. Save that. Compile. Run. Right, we'll roll 6 and 2. Dice sum is 8. Brilliant. Alright, now I want to embed a special value in my program. C has a slightly unusual way of doing this. It's a slightly old-fashioned way, but for our course it works well enough. So let me show you that. If I want to have what would often be called a constant value, because unlike a variable's value may change through the execution of a program. We can store different things in a variable as the program executes. If I want a constant value in my program, there is a way to associate a name with it. Let me show it. The syntax is old-fashioned, a little weird. I say hash define. You're saying, oh, that looks a bit like a hash include. It's not a coincidence. Hash define and then a name. Now, you can use any name, but to make it easier to understand the program, when we hash define names, we always use uppercase. So let me spell secret number properly. We'll make the secret number 9. That means anywhere we want to have the secret number in our program, we can now use the name secret number. It's a big deal. Actually, no, it's really, really crucial. Perhaps we want to use that value 10 places through our program, and then later we want to change it. Then we'd have to remember the 10 places through our program. It also makes our program more readable because we can put meaning with the name that the bare number doesn't have.
It's worth noting, just briefly, that this is not the same thing as defining a variable. The difference is sort of slight, but often people get confused and think that hash define is a new type of variable. It's not. I don't know whether Andrew's going to go into more detail about it right now, but hash define is actually just creating a constant, so it can't change, and there are some slightly different rules. So don't think it's the same as being like int secret number. It's not quite the same thing. You're just creating a constant that can never change, and that's why we use hash define as opposed to something else like secret number equals 54.
All right. Yeah, so there's the difference Tom was talking about. A variable, I can put any value I like in it. And as the program executes, it can be given different values through time. Every line of a program, I can update it every line of a program I like. So that an integer variable might contain 1, and then I can assign 5 to it, and then I could set it to 10, to 27. I can set it to different values. Secret number is just a name for this constant value. This makes no sense at all. And the compiler says, you can't do that, Andrew.
There's a really good question in chat as well, which might be worth addressing, which is previously we've said, int dice 1 equals whatever, or double dice 1. How does C know what type secret number is? Because maybe it might be a double, it might be a single or an integer. And the trick here is that what C is actually doing here is it literally looks through and replaces any time you say secret number with the number 9. And because it does that, if it's 9, it's just going to assume that it's an integer in most contexts. But if you had said, for instance, 9.0, it would assume you were talking about a double, because just like how we saw that earlier with 9.0 divided by 5.0, assumes it's double, whereas 9 divided by 5 assumes it's int. Sorry if I've stole your thunder there, Andrew.
No, that's all good. Now we're a bit of an impasse. Oh, actually, I wanted to show you. Yeah. Just demonstrate a variable having different values. So there's putting line 18 gives dice sum a value, but then line 19 gives dice sum a value, and then line 20 gives it a value. And when we get to line 21, we print out the current value of that, which will be whatever dice 1 was. So that's a very different program. Sorry. So if dice 1 is 1, dice 2 is 5. Yeah. So that's showing you the variable value changing. Doesn't make a lot of sense yet. Well, there's no importance to it yet, because you haven't seen, until we see some more C constructs, then it becomes useful. Right. But now I'm sort of stuck. From what I know, I can print out the sum of the dice, but I can't. I could print out the secret number, I guess. I could try that, but how do I do something based on that? And we need a new C construct. And new C construct, which we'll come back to at the start of the next lecture and go into more comprehensive details. But the new C construct is an if statement. So far, everything we've seen so far just says execute this statement, execute this statement, execute this statement, execute, execute. So it's just straight line execute. Line 10, line 11, line 12, everything gets executed as the program executes. An if statement gives us the possibility to have lines of the program executed only under certain circumstances. There is what I'd call the syntax, the pattern, if you like, of an if statement. We've got to fill in a gap here, a condition there, curly braces that surround the statements that we're saying only do these ones under some circumstances. So let's try them out. Now C gives you comparison operators, and again we'll go through these comprehensively at the start of the next lecture, that let you compare values. So we'll say if, and the comparison for quality is 2 equal symbols. That's one to remember. Yeah. It's quite confusing because assigning a value looks so similar. They mean very different things, by the way. Double equals is what a mathematician means by equality. Single equals doesn't really come up in mathematics much. You don't really assign values much in maths, unless you're Alan Turing. Alright, so if dice sum equals 0, we can put another one. It's a bit long. Let me shorten that to make that a little bit clearer. Okay. Ooh, and I forgot a semi. Every C statement needs that little semicolon. You're saying why? Why? It was perfectly obviously what you meant there, Andrew. Why couldn't the compiler just figure that out? It could, but do you really want that? If you're writing C code for a pacemaker and there's a slight error, do you want the compiler to take its best guess and keep going? There are certainly situations where you might want that. The classic one is web pages. The source code, the stuff, the equivalent of C, HTML behind web pages, almost always has errors. But web browsers just do whatever they can to show you, you want to look at kitten pictures online. You don't want to be told there's a tiny error in the web page. C programs is a different context. You want to know about tiny errors. Alright, so we enter 4, we enter 5, and you'll notice the printf didn't get executed. 0, that should not happen. Alright, so let's make the dice sum 0 and see if we can get the printf executed. I know, I'll enter a negative dice value. Can you have negative dice value? I'm sure you can have negative dice values. Well, it's just whatever's written on the dice space. And there we go. That was executed there. So we've got conditionally executed statements. May not seem like much, but we really only need one more thing, well, perhaps two more things to get everything that Alan Turing had in the 1930s in his model of computation. Two more things. But we're a long way towards that, towards being able to write any program. Alright, so I can put secret number there now.
There's a great question here, which might be just worth highlighting. It's asked, can we use if statements now to check if user input is valid?
Oh, you so could do that. I'm not going to do that, but you could do that yourself.
It might be worth noting at that point, if you wanted to check whether a user's input was valid, one way you could do it is you could decide on every single possible valid input, maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and write 10 if statements that said, if dice sum equals 1, dice sum equals 2, and you checked each one. But unfortunately, that's going to take up 30 lines of code. So there are other comparison operators that you can use that will come up. So we've already seen equals equals, which is asking if one number is equal to another number. But you could also say something like greater than, which is a what is it? Left angle bracket, I think. Where if you think about like an alligator, the open side of the angle bracket is the larger thing. So it's checking is the left-hand side bigger than the right-hand side, or you can check is the left-hand side smaller than the right-hand side. And so you can start to look at all of these different comparison operators, as we call them, and all of those are now available to you to use in the if statement as well. And we'll probably look at them a bit closer, I'd imagine, later or early next week.
Start of the next lecture, we're going to sort of take a step back and review comprehensively what the options in here. But it's easier if we're going forwards and showing the shape of the program, and then you can see all the possibilities. All right, so I think I have the program here that will let me roll dice and see if I can guess the secret number. I'm going to roll a 3 and a 5. Oh, nothing. All right, I'm going to roll a 3 and a 6. Oh, you rolled the secret my number. That's not very good grammar, Andrew. There we go. Imperfect grammar. I'll even add a full stop. Punctuation. Oh, that's quite nice. Be nice to give us a hint. So I could copy this, and Tom was talking about comparison operators. I can try them out. This is a bit beware. This is not the smartest way to do this. And we're going to come back to this, but let's show you. let's put Tom's comparison operators into. Let's give, if it's bigger than the secret number. Smaller than the secret number. So 3 if statements in a row. Now, yeah, what's worrying me is that these only ever one of these gets executed, and it seems a weird way to write it, and it is a weird way to write it, but it's using an if statement. So it's the if statements we've got, each with a printf in. So we'll try them out. So let's suppose I roll 2 ones. Let's suppose I get my act together, save the file, recompile my program, and roll 2 ones. Smaller than the secret number. I roll 2 sixes, bigger than the secret number. So I've mastered if statements. Actually, that's true. I probably have mastered simple if statements. There's more to if statements than this, but I'm pretty sure I'm doing pretty well here. Tom, can you have a scan of the chat and see if there are any good questions we'd like to address right now?
Absolutely. There's some discussion of the different operators that we can use, which is probably better saved for
next week. Yep. Yeah,
next
we're not
week.
going to tell you all the operators yet. You can look them up yourself, of course. I'm not going to stop you.
There's a question about style guide, in particular about if statements having curly braces on the same line. And I think the answer there is just this style is the course's preferred style. Apart from that, I think most of the questions have been answered.
All right. Style is a very vexed thing. We try to follow a consistent style in lectures and tutes. So if in doubt, many styles will work with the C compiler, but if in doubt, just copy what you see in lectures and tutes. Out in the real world, there are like 5 or 6 popular styles, popular ways to format lay out your C program. It doesn't change how it executes, just how it looks like on the screen, and at least as many more that some people use. So it's not as if there's one style, but we try to keep things simple for you, and until you understand some of the issues, just copy it the way we do it. Put braces there, across. Yeah, why did I put this across? Because I want to make it visually obvious to the human reading it that this is what's the case. Now, the compiler doesn't care. So I can, if I actually want, I could actually write the program like this. Let's keep going like that. Don't know how. So I could write it like that. It's a real mess. Really hard for a human to see what's happening there. But the compiler will do exactly the same thing with it. So we lay out the program visually to try and make it obvious to a human what's happening. So we indent. Yeah, you're going to hear this word a lot. We indent the statements within the if across 4 spaces so it's obvious to a human reading it. Tom?
There's also the eternal question, do we get marks for style?
Yes, and yes. So yes, we want you to write correct programs. That's incredibly important. But we also there are other properties of programs that are important as well as correctness, and that's programs that can be maintained over time, kept correct over time, modified when our needs for the program change over time, as they surely do. They're programs, and both of these things, well, even ensuring correctness, involves other people reading the program. So the ability for humans to read a program, either check its correctness, maintain it, modify it, the ability for other humans to read our programs is incredibly important. So we will assess you for that, and we will help you to learn how to write programs that are very readable. And as you do more coding, you'll discover you write. There's a very selfish reason to write readable programs, is that you won't be able to understand the program yourself. So you'll come back to a program you wrote quickly 3 months ago, and you have to change it, and you didn't sort of make it nice and easy to read, and think, oh God, I have to rewrite this. I just can't understand it. I even see it in exams. You see students are saying, I've got 45 minutes in the exam, I don't have time to indent things, and then they get confused about what their program does, and they don't get their question right. Whereas if they'd taken the extra 10 seconds to indent their program properly, they would be able to understand what their own program does that they wrote 30 seconds ago. All right. Oh, excellent question there from the Sheriff of Birds. I'm not sure it's a real job, but thank you for the question. What is this double equals doing? That's testing. So that's saying, is this value equal to that value? This one's saying, make this variable the same as this value. So that's saying, change dice sum. Get this value, put it in the variable dice sum. This one's saying, left-hand side, is that the same as the right-hand side? So that's comparing the two sides. Does the value in the variable dice sum equal the secret number, which is 9? Notice how easily now, by the way, is if I want to change the secret number, I can just go up here and change that and make the secret number 19, and it will change in all 3 places. Magic. All right, so that lovely little program is a nice step. We're going to take a step back, go through all the possible comparison operators, some variants on if statements. We'll even recap a bit what an int variable is, what a double variable is. We might revisit that nasty thing I bumped into. I probably should have tried to avoid that nasty issue with 5 divided by 9. Don't worry about that. That was sort of a little booby trap that we walked into. We'll also revise that in next Tuesday lecture. But our time today is at an end. Let me again apologize for not having anything resembling lecture slides up. I'll get lecture slides up as soon as I can, which may not be until, we'll see, I can get them up tonight or tomorrow morning. I'll pop up lecture slides covering this and going into Tuesday's lecture. So you will have a lecture slides and example programs. One more thing I'll do for you in future lectures, I think we can put the programs somewhere where you can access them, and we'll just give you a little URL where if you're super keen, you can fetch the program I'm writing or I've just written and compile it yourself, say on VLab in another window as you listen, and perhaps run it and change it and things like this. So if you're super keen and want to play along, we'll see if we can set it up so there's a URL where you can grab the not change, read only, grab the programs as I write them. Unless Tom has something urgent that can't wait until next Tuesday, we're going to sign off.
No, thanks very much, everyone. Have a good afternoon, weekend, and we'll see you all next week for another fun lecture of COMP1511.
Thank you, Tom. Thank you all for attending.